9.6 Lesson 3, the ratio and root test. Our objective for today is given a power series, such as this one here. What is a power series? In a power series, you have a variable x, which represents some constant. So for example, x could be 5, x could be -3. X is just representing some arbitrary constant. That's what makes you have a power series. Now we will be looking at the definition of a power series in another lesson, but that's what we're really talking about, where x is representing some constant value. Given such a power series, you will be able to find the values of x. So when x is what constant will the power series converge? And we will determine that by using something that we've learned about, the ratio test. Now when we look at the lesson on power series later, we will also be considering vocabulary such as radius of convergence and endpoint convergence, but we'll see this today. We will save this particular vocabulary term for later. There's something called the center of the power series. In this particular one, it is centered at x is equal to -1. You might be able to see why that's the case, but we'll save that for later. But really, we want to find the values of x for which this power series will converge, and that's called the interval of convergence. So we'll look at this problem for our lesson today, and here's what we need to do. To determine the values of x for which this power series will converge, we have to use the ratio test. We will be using the ratio test to do it. So we will be finding this limit, and we basically want to answer this question. For what values of x will this limit be less than 1? Those are the values of x for which the power series will converge absolutely. For what values of x will that limit be greater than 1 or infinity? Those are the values of x for which the power series will not converge, because it will diverge. And for what values of x will this limit from the ratio test be equal to 1? And for those values of x, we have to do another test. We cannot come to a conclusion using the ratio test whether the power series will converge at those values of x for which the limit from the ratio test will be equal to 1. So this is what's going to be useful for us for determining the values of x for which the power series will converge. And this is something that we will have to do something else for, because we can't use the ratio test to come to a conclusion if the limit from the ratio test as n goes to infinity is equal to 1. So we begin number 89 by setting up this limit from the ratio test. So the nth term of our power series for number 89 is -1 to the n times x plus 1 to the n divided by n. So we need to take the limit as n goes to infinity of the absolute value of the quotient of the n plus 1th and the nth terms. So here is the n plus 1th term. Wherever you see n in the description of the nth term, you just replace with n plus 1 and divide that by the nth term, which is the same as multiplying by the reciprocal of the nth term, which we have here. So now we can simplify. The way you can simplify is, first of all, you will recognize that in the limit for the ratio test, we have the limit as n goes to infinity of the absolute value of the quotient of the n plus 1th and the nth terms. However, if you look at the nth term for number 89, n starts at 1, and for the denominator, it will always be positive because n starts at 1 and it goes up by an integer each time. And for the -1 to the n, that's going to give us either a positive sign or a negative sign. And depending on the value of x, x plus 1 to the n for n greater than or equal to 1 could be positive or negative. For example, suppose x were equal to -2, then x plus 1 would be negative 2 plus 1, which would be negative 1. So if you have x plus 1 to the n, and x is equal to negative 2, then depending on the value of n, the x plus 1 to the n could be positive or negative. On the other hand, if you have x is equal to something like positive 2, then you'll have 2 plus 1 is equal to 3, but of course 3 to the n will be positive for any integer n greater than or equal to 1. But the point that I want to make is because x can be any number, we really need to keep the absolute value for this particular factor, because depending on the value of x, x plus 1 to the n could be positive or negative. That being said, we can still get rid of this because we don't need that anymore. That's just either going to give us a positive 1 or a negative 1. So now we're able to simplify, but we can't get rid of the absolute value for the reason that we just mentioned, because of the x plus 1 to the n. But we can get rid of the negative 1 to the n plus 1 and negative 1 to the n. So what we're left with is x plus 1 to the n plus 1 times n, and n plus 1 times x plus 1 to the n. So that's what we're left with. So now we're just going to simplify further. We can rewrite x plus 1 to the n plus 1 using properties of exponents as x plus 1 to the n times x plus 1 to the first power. So we have a product of two powers with the same base. So when you add the exponents n and 1, you get x plus 1 to the n plus 1. What that allows us to do is cancel the common factor of x plus 1 to the n that's in the numerator and the denominator, giving us the limit as n approaches infinity of the absolute value of x plus 1 times n over n plus 1. And as I explained earlier, the reason why we had to keep the absolute value was because of the x plus 1 factor, x plus 1 to the n power factor. Because depending on the value of x, x plus 1 could be positive or negative, so we need to keep the absolute value for that part of the expression that we have. So we are going to restrict the absolute value to that particular factor. So we have the absolute value of x plus 1. We don't really need the absolute value for the n over n plus 1 part of it. That factor does not need the absolute value because, again, n is going to infinity and n starts at 1. The more important part is that it's going to infinity. So as n goes to infinity, here's what we can do. In this limit, make the observation that n is going to infinity. X is just some value, some constant. It can be any value, like x could be 5 trillion, or x could be negative 2.5 billion. But once you choose x to be 5 trillion, or negative 2.5 billion, or whatever you want x to be, once you choose it to be that particular value, it becomes like a constant. It's fixed at that chosen value. You could choose x to be any number, but once you choose it, it's fixed and you treat it as a constant in this limit because it is n that's going to infinity. So you treat the absolute value of x plus 1 as a constant, so you can factor out a constant from the limit, and that's what we're going to treat it like. So we factor out this constant from the limit, so it comes out here. And then we take the limit as n goes to infinity of n over n plus 1, which is of course equal to 1. Which is of course equal to 1, because you have a quotient, you have a rational expression here where the degree of the numerator and the degree of the denominator are both 1. So the limit would be the quotient of the leading coefficients. 1 divided by 1 is 1. So that limit is equal to 1. So we have just the absolute value of x plus 1 times 1, or just the absolute value of x plus 1 as I have written here. Now what is this? Well, go back to how we started here. It's this limit. It's this limit from the ratio test. And according to the ratio test, whenever this limit is less than 1, our series will converge absolutely. So we really want to just find out for what values of x, will this limit from the ratio test be less than 1. So what we've found from our work here is that this limit is the absolute value of x plus 1. So whether this limit is less than 1 depends on the value of x. So for what values of x will this limit be less than 1, and therefore our power series will converge absolutely? That's the question that we're trying to answer. So the way we're going to do that is we're going to take this limit, which we now know to be the absolute value of x plus 1, and set that less than 1 to find the values of x that would make this power series converge absolutely. So we're going to write our absolute value inequality as a compound inequality. So we're able to write the absolute value of x plus 1 is less than 1 as the quantity x plus 1 could be anywhere between -1 and +1, because absolute value is saying that this quantity x plus 1 is less than 1 unit away from the origin on the number line. So we can represent that with the picture that we see here. So now that we have that, we can solve for x by subtracting 1 from each part of this compound inequality. And when we do that, we get x is equal to, x is between -2 and 0. But we can't complete the problem by stopping here. And the reason for that is as follows. What is the absolute value of x plus 1? It's this limit from the ratio test. Now we know that when that limit is equal to 1, the ratio test is inconclusive. And the values of x that would make that limit equal to 1 are at x is equal to -2 and at x is equal to 0. So you have the absolute value of x plus 1. If x is equal to -2, that would be equal to 1. So that limit would be equal to 1, and therefore the ratio test would be inconclusive if x is equal to -2. The same thing happens when x is equal to 0. If x is equal to 0, then that limit that we found for the ratio test would be equal to 1, and we can reach no conclusion based on our work using the ratio test. So we have to do some other test at those two values of x to see if the power series may converge or diverge. And that's the work that we'll be looking at now. This is called testing for endpoint convergence. So let's see what happens when x is equal to -2, and let's see what happens when x is equal to 0. So what you have to do is you have to go back to your power series, which we have for number 89, and you're just going to replace the x in the power series with -2 and see what you get. So let's look at that. So when we replace x in our power series with -2, this is what we have. And of course we can simplify -2 plus 1, which is equal to -1, so we have -1 to the n. And we have the -1 to the n that we had from the very beginning of the problem. And we have the n that's in the denominator of the nth term from the very beginning of the problem. So now we can do something with the numerators here. You have -1 to the n times -1 to the n. Using this property of exponents that I'm highlighting here in gold, if you have a to the n times b to the n, you can write that as a times b to the n. So we're going to write -1 to the n times -1 to the n as -1 times -1 to the n. -1 times -1 is +1, so what we have here simplifies to 1 to the n, which is of course 1 for any value of n. So when x is equal to negative 2, the power series for number 89 becomes the harmonic series, or a p series with p is equal to 1, and therefore the power series will diverge when x is equal to negative 2. Notice that we come to this conclusion that the power series will diverge at x is equal to negative 2 by using the fact that we have the harmonic series, or a p series with p is equal to 1. We're not using the ratio test to come to this conclusion because at this value of x, as we explained earlier, the ratio test is inconclusive. So let's take a look at what happens at the other value of x that makes the ratio test inconclusive at x is equal to 0. So here is what we see with what's happening with the power series when x is equal to 0. So we replace x with 0, and we get, for this factor x plus 1 to the n, when x is equal to 0, that just becomes 1 to the n, which is of course just 1 for any value of n. So our power series becomes negative 1 to the n over n when x is equal to 0. And this is an alternating series. So to determine whether this alternating series converges or not, we will be using the alternating series test. So to do that, we have to check for these two conditions from the alternating series test. The limit of a sub n, which is 1 over n as n goes to infinity, is that equal to 0? And it is. And then we have to check to see if a sub n plus 1 is less than or equal to a sub n for n greater than or equal to 1 or some other integer. And it does happen to be the case. When you check that, it's very easy to verify. So we conclude that the power series converges when x is equal to 0 by the alternating series test. Now we may state our conclusion about what we call the interval of convergence, the x values for which this power series will converge. So we were able to come to the conclusion about that x has to be between negative 2 and 0 for it to converge by using the ratio test. But for x is equal to negative 2, we had to do additional work because the ratio test was inconclusive at x is equal to negative 2 and also at x is equal to 0 because the limit from the ratio test would be equal to 1. So we were able to determine that when x is equal to negative 2, the power series would diverge, and when x is equal to 0, the power series would converge. So when you look at the interval of convergence, it does not include negative 2, but it does include 0. So that's called the interval of convergence. These are the values of x for which this power series will converge. And we were able to make that determination by using the ratio test and also by using the p-series test and the alternating series test to check for convergence or divergence at the endpoints where the ratio test was inconclusive. So today we looked at the power series for number 89, which is the one from the objective, and we were able to find the values of x for which the power series will converge by using not only the ratio test, but we began with the ratio test, but we also had to check for convergence at the endpoint by using other tests for convergence or divergence of series.